Hi, my name is Jason Radzizewski.
I'm Tyler Burnett.
And I'm Eric Weber.
And we did a sensor-based timer for our senior design project. And our advisors were Dr. Rajesh Kadasari and Jeff Erickson. A little bit of background information in our problem statement is that both of our advisors, Dr. Kadasari and Jeff Erickson, were both having a problem with their long-term procedural processes that they were doing. And one of the things that they ran into is it was mainly they were running out of time, they didn't realize what step they were at, or they missed the sensor alert as far as the measurement values. So they were looking for a device that would measure the values, alert a user when one of their sensor ranges was out of range, and then also from that point too, look at the timer value to see when is their timer expiring.
So, introduction to the device. It's a long period timer with multiple programmable segment lengths, and it shows the segment on an LED light bar. It flashes the current segment and shows the previous segments lit up. It's 4 sensors for measuring temperature, humidity, alcohol, and a bubble counter for measuring CO2. The sensors have programmable ranges and will alert if they are outside of acceptable values. The device alerts on that as well as if a timer segment is complete. It has a battery backup to keep powered while power outages. Block diagram of the device. Our power circuit is, everything's powered by 5 volts. Comes from either the wall supply or the battery. We have an automatic switching supply that switches if we lose the wall supply, and goes to a voltage regulator to regulate it down to 5 volts. Our inputs for our device are keypad, a temperature sensors, and the keypad goes through an encoder to save pins on the PIC. The temperature sensor uses an instrumentation amp to get better resolution, while the rest of the sensor, while the humidity sensor and alcohol sensor use other analog inputs, and the photo interrupter is a digital, either something's in the way or something's not. The outputs of the device are a segmented LED bar, LED alert bar and buzzer, and an LCD display for displaying the user interface. Tell you a little about the sensors. The temperature sensor reads temperatures from -10 degrees C to 40 degrees C. The output is put through a differential amp, that instrumentation amp that will gains it to 0 to 5 volts to get better resolution on the input. The humidity sensor outputs a voltage that corresponds to 0% humidity to 100% relative humidity. This voltage is linear with relative humidity. The calculations are done in the microcontroller. The alcohol sensor is a resistor sensor that's calibrated to give values from 0% alcohol to 100% alcohol. The resistance of the sensor decreases during the presence of alcohol, and that's detected through the digital analog to digital converter. The photo interrupter is used as a bubble counter, and it counts bubbles passing through an airlock, and it counts in bubbles per minute.
So the keypad on our device, we use a 4x4 keypad with numerical values and 6 alphanumeric values. So we use 6 functions for each of those, A through F. We use these functions assigned to them are start and stop, reset, skip, confirm, mute, and toggle low power mode. Our keypad, we send it through the MM74C922 encoder, which allows us to convert it into a binary value without having to use too many pins or constantly cycle through rows. The LCD display we use a graphic display with a resolution of 192 by 64. The display uses an 8-bit bus to receive data. We write to it using commands all written in the PIC, complete with a few commands to draw different things, including pixel by pixel or rectangles, and we have both digits 0 through 9 and capital letters A through Z. So the software, we use a PIC 18F4620 microprocessor. The PIC, we program it in C, and in it we have this flowchart here, which covers the main function and how we move between different stages, including selecting different modes between sensor mode, timer mode, or sensor timer mode. So the code implements a few functions, including inputting all of our sensor and timer values, including time for our segments and the upper and lower limits on all of our segments. Most of the functionality from the code is involved in writing data to the display.
So for the LED bars, there's two different kinds. We have one that is an alert bar that also uses a buzzer to alert the user whenever there's a sensor value out of range or a timer segment is complete. And then we also have our segmented bar, which shows the progress of time throughout the entire project. Each bar has about 12 RGB LEDs in it, so that's a total of 24 for the entire two set. And then the timer bar has 6 segments that are programmable and show the range of when you are in the project, as well as the colors for each one are set with fixed resistors, so they do not change. We had been looking at doing pulse width modulation, but with our microcontroller and our limited number of pins, it was not possible. And for turning on and off the lights, there's a signal that's sent from the microcontroller to a JFET, which in turn allows the current to flow. This is our final device. We have a photo of our enclosure, both front and side. We have our screen, our keypad, and our LEDs on the front, and then we have our power switch and our power jack on one of the sides. The 3D enclosure is composed of originally 3 pieces, and due to printing error, we had to increase that to 4 for the back panel. So this is the inside of the device. As you can see, the back of our PCB is in there with all of our main components that need to be accessible, such as our potentiometer, our chips, and our voltage and power supplies. We have our backup battery that also sits within the case that works with a charging circuit. And then we have our top and bottom of our PCB. On the top, which we use as the front, we have our screen, keypad, and our LEDs. So that's just what we have mainly on there, as well as most of our routing, so that doesn't interfere with the back of our board. And on the back of our board, we have all of our other componentry.
Some problems and lessons learned is we had an overheating voltage regulator that caused our voltage rail to drop and caused issues with the screen. We ended up remedying by buying a heatsink. Working with the PIC, we had a limited number of pins, and this influenced some decisions like using the encoder, selecting a screen that could be used with the PIC, and eliminating some other functionality like separate buzzer and alert bar notifications. Another issue is getting the photometer to work. Passing bubbles can be kind of hard to detect. We end up using colored water and increasing the sensitivity of the photometer to be able to capture these bubbles.
So here's our budget and the retail price. Overall, we kept the price down to about $255.95. That's total all parts used in 1 unit. So overall, we stayed under budget using only 220 of our 400 allotted budget. Our requirements, we met all of our requirements, and really the only issues we ran into were some small issues with refining the enclosure and adding a few final touches.